In this video, I will be going through the solution to electric field practice sheet number 2, problem number 3. The problem states, determine the electric field E at the origin in the diagram shown below due to the two charges A and B. With the diagram in place, first thing I'd like to do is just draw the electric field vectors. I'm also going to label this, we'll call this Q1, and I'll call this one Q2. Just for a little ease of labeling. And Q1 is a positive, Q2 is a negative. So at the origin point, the electric field due to charge 1 is going to be going down away from charge 1. So I'll call that E1. And here, Q2 is a negative, so the electric field will be going towards Q2. That's E2. My next task is to actually figure out what those values are. Eventually we'll put them together, but first let me find out what those values are. So I use the electric field equation for a point source. E1 equals K times Q1 over D squared. K is 9 times 10 to the 9th. Q1 is 26 microcoulombs, which is 10 to the negative 6, divided by 8 centimeters. 0.08 squared, and that answer is, let me look it up, 36562500 newtons per coulomb. It turns out that we could do this work again. However, if we look at the numbers, the Q is the same, the charge is the same for charge 2 as it was in charge 1, so the magnitude of the charge is the same, and the distance between the points is the same. So the electric field strength, magnitude, the direction is different, but the magnitude, the size, is the same. It's 36562500 newtons per coulomb. Eventually these two will add up to get our resultant vector. But first, E2 is a little bit tough to work with, so what I want to do is I actually want to take that and I'm going to break it into its components. I'll do that work green here. E2 kind of looks up like this. And, it has two components. It has an X component, which is called E2X, and a Y component, which is called E2Y. This is E2. This angle, if we look at this angle, this is an equilateral triangle, which means this is 60 degrees, so that would be 30 degrees. So we have a 30-degree angle. I'm going to start by finding the X component. Cosine of theta equals the adjacent side, E2x, over the hypotenuse, E2. E2x equals, next line down on the page, E2 cosine theta. E2x equals 36562500 times the cosine of 30. And after doing the calculation, and you can pause the video if you'd like to do it on your own, which I suggest. I think that's a good habit to get into, plug in the numbers on your own. But that number comes out to be, I'm going to look it up, I had done the work beforehand, but it's 31664053.8259. And depending upon how much you round, you may get a different value at the end of the problem. I'm also going to repeat the procedure for the Y component. Now I'm using sine, E2Y over E2. And this would be E2Y equals E2 sine theta. E2Y equals 36562500. That's a sine of 30, which is half of that E2 value. And we should get 18281250 newtons per coulomb. And with these two, now we're dealing with three vectors. We're dealing with E1, E2x, and EY. And what I want to do is I want to think about all the electric fields in the x direction. And there's only one. That's E2x. And in the y direction for the electric fields, I have one going down, which is E1, and I have one going up, which is E2y. If you look at this, E2y value is going up. So I'll have to subtract those. And this is going to give me my net electric field in the x direction. Y equals E1, which is 36562500 minus my E2y value, 18281250. My EY value is, I think it comes out to be the exact same thing, but I want to make sure. 18281250, which it does. So now I have an E2, I have an EX value and an EY value, and this is the final part of the problem where I put my EX value together with my EY value, and the resultant will be the net electric field. And for that, I'm going to use the Pythagorean theorem. The thing about components is it does take a little bit more work, but in the end, you're always dealing with a right triangle, which is something that I find kind of easy. There's other ways of doing this. You could use a non-right triangle, definitely, but for this work, it's E net squared equals EX squared plus EY squared. E net equals the square root of EX squared plus EY squared. The net electric field equals square root of, let's gather these numbers, it's 31664053.8259 squared plus, extend that radical there, 18281250 squared, and the net electric field is 3.7 times 10 to the 7 newtons per coulomb. Now that value, I believe, when I did it in my calculator, came out to something more like 3.65 times 10 to the 7, but we're just going to round at the end here. If you're close to that and you follow this work, you're on the right track. The final thing to do is find this angle. So I'll do that over here. Substance space. Tan theta equals EY over EX. Theta equals arctan, tan inverse, EY over EX. Tan inverse of EY was 18281250 divided by 31664053 point. I can't fit it on the screen, but you can pull the number over. And that angle was 30 degrees, which turned out to be really nice. So at 30 degrees, and this is, if you go by north and east there, that's south of east. And I'll box my answer. And there you have the solution to challenge problem number 3.